Okay, so we started this lecture on concentration units in class on Wednesday, and we went over molarity. And you guys, just as by way of reminder, because this is really important, anytime you see or hear capital M, which stands for molarity, you should instantly translate that into what? Yes, moles per liter. It's very important because while molarity looks nice, moles per liter is actually useful with dimensional analysis. And guaranteed, if I give you molarity, I'm asking you to do dimensional analysis. So the term molarity, not so useful. Moles per liter, quite useful because you have the dimensions to do the analysis with. So yes, I'm so glad that you guys are all really quick on that. Moles per liter, very important. So that's the first one that we talked about, and in class on Wednesday, we did this first page of our in-class activity sheet, and we calculated things in moles per liter. And then if I gave you molarity, which then you guys instantly had to translate into moles per liter, then you could do these other conversions into, say, grams. If I gave you liters, because then you could use the liters to cancel out the liters and the moles per liter, and then you could convert from moles to grams because you know how to do that. So that's what we did with molarity, and there's going to be a few problems like that on the exam. So make sure that you know your way around the moles per liter and the molarity, and we're going to see that again on exam 5. So big deal, big deal. Make sure you know that. Okay, all solution concentration units, again, have to do with the amount of solute in your solution divided by your amount of solvent. And so molarity is using your amount of solute in units of moles and your amount of solvent in units of liters. But we've got a number of other solution concentration units that we need to be aware of and be familiar with using. So the next one I want to talk about is percent concentration. And percent concentration, as in 100%, basically tries to tell you how many parts per 100 are your solute. And percent concentration always uses units of either grams or milliliters, one or the other. Oh, I'm sorry, back up. This is not amount of solvent. That's the amount of your total solution. I should specify. Total solution, not your solvent. C. Newland wants to know if I'll help with this section up here, because we did this one in class on Wednesday. We can talk about it once we're done with our lecture today, but I don't want to go over it again right now because we did, I think, go over it in class on last Wednesday. So we can come back to that in a minute, but I want to make sure that we cover the new material first. But yes, I would be happy to go over it. Okay. All right, so, all right, back to solution concentration units. So percent concentration uses units of grams and milliliters, and the reason that it does is because for water, 1 gram is equal to 1 milliliter. That's the density of water. And so if everything is in either grams or milliliters, then everything's in essentially the same relative unit size, and so that gives you a good way to compare amounts of each and call it a percentage. And so for sometimes in percent concentration, you might see this given as weight percent, which is usually grams of solute over milliliters of solution or grams of solute over grams of solution. Or it could be given as a volume percent, which would be using milliliters of solute over milliliters of solution. And kind of which one of these is used depends on whether if your solute is a solid, then it's going to be easier to weigh it out as grams. Whereas if your solute is a liquid, then it's going to be easier to weigh it out as milliliters. So that's going to be kind of the difference between why you might use volume percent versus a weight percent. So let me give you an example. At the store, you guys will easily find solutions of 30% isopropyl alcohol, and they don't say what it's in, but you can assume that it's in water. So 30% isopropyl alcohol in water. So if I'm 30% isopropyl alcohol, then how much of my solution is water? 70%, so that would be 70% water. So isopropyl alcohol is naturally a liquid if you had like 100% isopropyl alcohol. So do you think that this 30% solution, do you think that that's given as a weight percent or a volume percent? This is a volume percent. And they may or may not state that explicitly, but it's a volume percent because, again, isopropyl alcohol is a liquid. So if they specify, you'll see this little V per V to say it's volume over volume, just to specify so you know isopropyl alcohol. So the way you would make a 30% isopropyl alcohol solution would be to take something like 30 milliliters of isopropyl alcohol and add it to 70 milliliters of water. And between the two of those, you should get a solution which has then, if we're looking at percentage concentration, 30 milliliters isopropyl alcohol, that's your amount of solvent, divided by 100 milliliters of solution. And then we're going to multiply it by 100 to make it a percent. And that's how we get 30%. Okay, so your percent concentration takes grams per mils, grams per grams, or mils per mils, and then multiplies it by 100% to make it your percentage of concentration instead of your fraction. Because without the 100% down here, it would just be 0.3 would be your fraction of the two. Is that kind of making sense? The way you're going to calculate percentage concentration? So the actual formula might be grams of solute, and I'll say, or milliliters, divided by usually milliliters of solution, but it could be grams, and then multiply it by 100%. That gives you your percent concentration. Any questions before we look at the in-class activity sheet? We're going to do a couple examples there. But is there anything in this page that's not making sense right now? Or if you're with me, say, I'm with you. Because I don't want to move over until I'm sure that at least two of you are with me. Okay, excellent. Okay, let's do a few of these. So in our, let's see, 9.1 in-class activity sheet, here then, weight percent, and W over V tells you weight per volume, or W over W is weight per weight. Okay, and here we're going to assume that the solution volume is the same as the solvent. That'll be true for very dilute solutions, but not necessarily for concentrated ones. But to keep it simple, then we're going to assume that the two are the same. So here, in this first example, I gave you moles of your solute and liters of your solution. So the first thing we're going to need to do then is convert to the units that are appropriate for weight percent, which is what? What are the units I need those to be in? Grams. Can't use moles, I have to use grams. And I have to use milliliters, not liters. All right. So I can convert this to milliliters. This should be 5,400 milliliters. You guys should be really good at those conversions by now. To go from moles to grams, I'm going to need, let's see, 12 times 6 is 72, plus another 12 is going to be 84, plus 6 times 16, that's just making me think too hard. So 6 times 16 plus 84, okay, molecular weight of 180. So 1.25 moles, 180 grams per mole, and this is glucose, glucose, glucose. My moles cancel, and I can say that I have 225 grams of glucose. What do I do now? Perfect. I've got my grams and I've got my milliliters. So I want to put my solute on top, which is the grams of glucose, and my solvent or solution on the bottom, which in this case is 5,400. So that gives me a fraction, 225 divided by 54. Okay. That gives me 0.0417. Then what do I do? Times it by 100 to make it a percent. Perfect. So if I multiply that by 100, I find that this solution is a 4.17% solution of glucose. Is that pretty straightforward? Okay. This next problem is identical because I give you moles and liters, so you're going to have to convert to grams and milliliters exactly like you did here. I'll let you guys do it. These next problems are even easier because I gave you grams to start with, and then you can convert to milliliters, and then you proceed as above. So I'm going to let you guys practice these on your own because by doing so, you're going to get better at it than if I do them for you. But I'll do one of these ones, okay? What does it mean that I've got this capital M? What do I do with that? Yay! You guys are exactly right. Capital M is molarity, which means moles per liter. So before you do anything else, you can translate that and say, okay, this is actually giving me 0.150 moles of my KBr for every 1 liter of my KBr solution. Okay, well, that's useful as a unit of molarity. How am I going to translate that to weight percent? Yeah, convert moles to grams using the molar mass. Okay, so I'm basically doing the same thing I did up here, but here I gave you moles and I gave you liters, so it made sense to convert those to grams and convert those to milliliters, and then I could plug it into the formula. Here, instead of giving you a volume, because I didn't, I just gave you a concentration, but the concentration is in 1 liter. So now I just do the exact same thing I did up here, convert from moles to grams, and from liters to milliliters. And then once I get the grams and the milliliters where I want them to, then I can multiply it by 100%. I hope that kind of makes sense. It does tend to confuse students that there's no volume given here, but that's because I've given you a concentration, which is appropriate for a volume. You know, you could just set it to a volume of 1 liter and call it a day. So first thing, molar mass of KBr, which is 120. 119 grams per mole. So molar mass, 119 grams of KBr in 1 mole of KBr. So moles of KBr cancel. So I've got grams. What do I do next? Dimensional analysis style. Setting this up to get the units I want where I want them. Yeah, but I'm not done. I'm not done because I have grams per liter. Liters to milliliters, because I need everything in either grams or milliliters. That's the key with all of my percentages. Okay, so, all right, 1 liter, 1,000 milliliters. Okay, now I have all the units that I want, where I want them. Now I can do all my multiplication, division. So I'm going to find that I've got 0.150 times 119 divided by 1,000. Okay, what do I do next? This is the fraction of, this is the number of grams of potassium bromide in a milliliter of my KBr solution. And Brooks is exactly right. Multiply it by 100 to make it a percentage. So this solution is a 1.79% solution of KBr. Did you guys follow me there? Excellent. Excellent. Okay, well, let's do this next section. So section 4 was weight percent. So I was using grams on top and milliliters on the bottom. Now section 5 wants you to do volume percent. So V over V means I'm going to be using volume on top and volume on bottom. So what are the units that I'm going to need to do for this percentage question? All of my percentages use either grams or milliliters or both. But in this case, because it's telling me I'm using just volumes, we know that milliliters is the unit of volume we're going to be using. Since this is a unit of weight, we don't need to use it. Excellent. Okay, so in the first case, I've got 1 liter of solution, 450 milliliters of ethanol. So how should I set this up in my equation to get the units that I want where I want them? Oh, Candace is on top of this. So she says, I don't want to use 1 liter because I need everything in milliliters. So I'm going to make that 1,000 milliliters. My solute needs to go on top, so that's going to be on top. I'm going to shorten that to ETOH, which will make sense to you guys next semester. Over 1,000 milliliters of total solution. Then what do I do? Oh, perfect. Megan's got it. Then I multiply it by 100 to make it a percentage. And that's going to give me a 45% alcohol solution. Should say 45% CH3CH2OH. Was that pretty similar? Pretty straightforward? You guys think you can do this second example on your own, this H2SO4? Yes, okay. Okay, I'll let you guys do that. It'll be good practice. Okay, section 6 takes us to our next section of solution concentration units that you need to know from the second lecture. And this is units of parts per million or parts per billion, both of those. Sorry, I had to sneeze. I'm a little sneezy today. So if you see me cutting out my microphone, it's because I don't want to blast your ears with that. Okay. Oops. Okay. So parts per million or also parts per billion and or actually I should note, by the way, we cover several different types of concentration units in this class, and they're all used kind of in different situations for different things. So we talk about molarity because this is what chemists use all the time, and that's why we're going to see it again in chapter 10 as a way, and chemists use it because we're interested in mole ratios kind of a thing when we talk about reactions, as we learned in chapter 6. And so, of course, chemists like to use a unit of concentration that has moles in them. Percent concentration is something that you guys have probably seen in lots of places, and it's easy to use because it's very accessible. It's easy to weigh something in grams, and it's easy to measure something in milliliters. And percentages are something that most of the population has some experience or understanding of. So that's why most of the stuff on the shelf at the store, like your hydrogen peroxide solution or your isopropyl alcohol solution, or maybe even reporting the amount of benzoyl peroxide or salicylic acid in your facial medication, all of that's given in percentages. So you guys should be pretty familiar with those. Parts per million and parts per billion are useful in cases where your concentration units are just so tiny, very, very tiny. But that doesn't mean that it's negligible, okay? Because some of the things that we measure in, for instance, our drinking water could be very harmful at concentration that is higher than just a few parts per million or even a few parts per billion, because some of these dissolved solutes might just be that toxic, or it might just be that they will accumulate in the tissues until they become toxic. So these are often used for solutions that are very, very dilute, have a tiny amount of solute. Now, the formula for parts per million or parts per billion is actually going to look really familiar, because just like percentages, we're going to use grams and milliliters, okay? Weight of our solute over volume of our solution, or weight of our solute over weight of our solution, or volume over volume, exactly like here. The difference is that percentage concentration is essentially telling you how many parts per 100 are your solute. In other words, when I say I've got a 30% solution, then I know that 30 parts out of 100 would be my solute. So the parts per million and parts per billion actually follows this exact same formula, but instead of multiplying it by 100 to make it a percentage or to represent parts per 100, what do you think we multiply that equation by to make it parts per million? A million. Exactly. 10 to the 6 is a million. What if I was calculating parts per billion? What would I multiply it by to make it parts per billion? You multiply by a billion, which would be 10 to the 9th. That's exactly right. Okay. So for example, and I'm pulling this directly out of my lecture notes here, if you've got tap water that is fluoridated. Oh, here, I'll write this down. So this is grams of solute over milliliters of solution. And again, could be grams or milliliters, top to bottom. Then multiply it by 10 to the 6th, gives you parts per million. Or multiply it by 10 to the 9th, parts per billion. Okay, so let's say we've got tap water and it is fluoridated, and you've got 32 milligrams of sodium fluoride that they're using to do the fluoridation in every 20 kilograms of solution. So the question then is, what is my concentration in parts per million? What would you do to solve that problem? Perfect. Convert each to grams first, because everything needs to be in either grams or milliliters. That's the cardinal rule for percentages, parts per million, parts per billion. Grams or milliliters, milliliters or grams, but I have to be in grams or milliliters because otherwise, no good. Okay, so convert those to grams. 32 milligrams, 1,000 milligrams in 1 gram. That gives me 0.032 grams sodium fluoride. And then in this case, 20 kilograms. And we've got, again, 1,000 grams in 1 kilogram. Okay, good. So that gives me 20,000 grams of solution. Excellent. Now what do I do? Excellent. We just take the solute, which in this case is sodium fluoride, so 0.032 grams sodium fluoride, divide it by our solution, which in this case is 20,000 grams of solution. You can tell this is going to give us a very tiny number, which is why it'll be useful then to multiply it by 1,000,000. And when we do that, what do we get? Should get 0.16 parts per million sodium fluoride. If you got 1.6, it sounds like you were putting everything into your calculator and something in the way that you put it in made it multiply by an extra 10. So you should definitely play around with your calculator and figure out what that is to make sure that it doesn't do that on an exam. But let's see, 0.032 divided by 20,000. And I'm going to multiply that by 1 times 10 to the 6th. Oh, see, I did the same thing that I shouldn't have done, I think. 0.032 divided by 20,000 times 10. Oops, that's not at all what I meant to do. This is why I use a regular scientific calculator and not the Windows calculator on my exams. you know what? I think Robin and LP are correct. If I take this and I multiply it by 10 to the 6th, 2, 3, 4, 5, I move that over by 6 positions, that should give me a 1.6 part per million solution. Does that make sense? If I stop and don't multiply it by 1 times 10 to the 6th. So I lied. I was going right off my lecture notes, which just said 0.16, and I thought, that must be right. Let's do that. There we go. 1.6. Okay. Should we do a parts per million one? Let's try this one again from the lecture notes. We want to calculate the concentration of chloroform in drinking water. So chloroform, known carcinogen, available in drinking water up to 100 parts per billion in drinking water. Let's go backwards. If I drink 400 grams of water, that's like a cup and a half. So the question is, how much of chloroform, that's CHCl3, do I get? Okay, this is going backwards, but it's a formula we can kind of plug it into. So the formula tells us that parts per billion is mass of our solute over mass of solution. So if I have 100 parts per billion, that concentration is my mass of solute, which is, that's what I'm looking for, X grams CHCl3, divided by mass of my solution, which was given right here, 400 grams of water. Here, we're going to assume that the additive mass of my CHCl3 in my water, my total solution, is the same as just the solvent because it's such a dilute solution. So 400 grams of solution. And then because this is talking about parts per billion, I'm going to multiply this by 10 to the 9th. Everybody see how and why I set that up the way I did? Okay, now we just solve for x using algebra, right? What are we going to do to solve for x? Excellent, excellent. You guys are both right. I have to multiply both sides. Oops, I'm going to do this in a different color. Multiply both sides by 400 grams. So that'll cancel that out. And I'm going to divide both sides by 10 to the 9th. Cancel that out. And that gives me my x gram CHCl3 all by itself. So 400 multiplied by 100 divided by 10 to the 9th. So easy way to do this. 400 times 100 gives us 40,000. And then, give myself some room here. 40,000 divided by 10 to the 9th. One property of exponents is that when you divide, it's like multiplying by the negative. So that's like saying 40,000 times 10 to the negative 9. So then we can move this over by 9 positions. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's where we put our decimal. So that gives us 0.1234 grams. There we go. So 4 times 10 to the negative 5th is what we should get. CHCl3 in 100 parts per billion that we started with. You guys with me here? If we plug this in, 400 times 100 divided by 1 times 10 to the 9th. There we go. 4 zeros and then a 4. Everybody following me here? It's literally exactly the same as percentages, but you multiply it by a million or a billion if you're looking at parts per million and parts per billion instead of 100, which is what we did with the percentages. Okay, so on 9.1 in class activity sheet, here, this is going backwards from weight per volume on a percentage. This starts with parts per million and it has you convert it to percent by mass and convert it to molarity. You can see what a tiny concentration this is compared to molarity and percent by mass. In this case, you get molarity and percentage, try to determine which one is the higher concentration. And then here, given parts per million, figure that out in percent by mass and molarity. Are there any of these that you want me to do with you before we move on? Okay, I'm going to do the top right one because I think this is one of the harder ones. And then beryllium one, it was basically the same type of question, so that'll be just fine. Okay, so maximum contamination level for arsenic in tap water is 0.010 parts per million. That's 10 parts per billion. That's the maximum you can get for arsenic in tap water because arsenic is considered to be toxic at all concentrations, essentially. So they just gave you the lowest, you could possibly. By the way, you guys might want to look this up and post about it, but apparently we found arsenic at higher levels than this in like boxed apple juice for kids and in rice. You guys should look at why that is and consider, should I maybe eat a little bit less rice or should I not be buying apple juice? It's kind of a question because if we don't want it higher than this in just the water that we drink, then maybe we shouldn't want higher than that in the juice that we drink either. So that's an interesting question, directly applicable to what we're talking about in terms of concentration units. And you might ask yourself, where do we get arsenic from? Like, how does it even get into our apple juice supply or our rice supply? So, good. Oh, that's interesting, Megan. There is cyanide in apple seeds or in apple cores, just like there is cyanide in peach pits. But it's at such a low concentration that most people don't worry about it. In fact, I've heard people claim that there's health benefits to that low level of cyanide. And so they swear by eating all the apple, including the core, every day. Must be so good for you. Almonds, not almonds, but the bitter almond flavor that you get from peach pits would be enough to potentially cause damage, but actually not apples so far as I've read about. So, and yeah, it's interesting. It's an interesting lesson to learn when we discover we've got all this stuff in our natural food. 100% apple juice. You're like, well, it's apple juice. What else could it have in it? Well, okay, it might have cyanide. It might have arsenic. And you have to ask yourself, at what level is that acceptable or not, depending. You will get water quality reports when you own a home, and you pay for your tap water. You'll get water quality reports on a regular basis that report the levels of arsenic in your tap water, among other heavy metals and other potential contaminants, every year, essentially. Water quality report letting you know what's in the water that you're paying for. So, yeah, interesting. It's interesting. All right. That was a bit of a tangent, but I think directly applicable. All right, so let's plug this in. We know that 0.010 parts per million is equal to the grams of arsenic in the milliliters of solution multiplied by 10 to the 6th. That's what that means, right? We can put an x here. Let's solve for x. And if we do, here we go, solve for x, 0.010 divided by 1 times 10 to the 6th, we'll see that that should be, what is that, 1 times 10 to the negative 8? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that should be. Okay, 1 times 10 to the negative 8 grams of arsenic in every 1 milliliter of solution. Now, this is what kind of freaks students out, okay? I gave you concentration, but I didn't give you volume. For some reason, students are like, well, I need the volume to make this work. No, you don't. Concentration is just a ratio of your amounts. So I don't necessarily need to know what the volume is. Here I could just operate on, let's assume I've got 1 milliliter of volume, because I'm only converting from one concentration unit to another concentration unit. Okay, so it's okay. You don't need to know volume. You just need to know the ratio, because that's what all concentration units are based on the ratio. And if you can get your units in that ratio to the right place, then you'll be fine. So now we know, we used that parts per million, we got rid of the part that made it parts per million. We know the ratio of grams of my solute per milliliters of solution. So now if I wanted to make that percentage by mass, what would I do to make that a percentage by mass? What units do we need our solute and solution to be in to make it a percentage? Perfect. You need it in grams and milliliters to make it a percentage. Well, that's easy. I'm already in grams and milliliters. So I'm going to divide. So I get, because I'm dividing by 1, I get 1 times 10 to the negative 8. But I need to do one more thing to make it a percent. Multiply it by 100. Exactly. take this value, multiply it by 100%, and I should get 1 times 10 to the negative 6th % arsenic, or 1, 2, 3, 4, 5. That's the percentage of arsenic in tap water. You can see why they use parts per million. They're like, you know, this 100% thing is not quite so useful. Okay. All right. And that works really well because remember, these are both essentially the same thing. The only difference between the percentages and the parts per million is what I multiplied it by. 100 to make it a percentage, a million to make it parts per million. So if I go backwards by dividing by a million and then go forwards by multiplying by 100, I'm done. Okay. We did. Right here. X grams of arsenic per milliliters of the solution by time multiplied by 10 to the 6th is the formula that gives us parts per million. And then if we just solve that formula for X, that tells us the number of grams of arsenic in 1 milliliter. It's possible. It's possible. That's the easier one. How do we do that? What do we do now if I wanted to convert this to molarity? Oh, it's not that bad. These are formulas. You guys love formulas. Every day you guys are like, no more dimensional analysis. Just give me a formula. Let me plug it in. Oh, Jay Houston says, well, why didn't we use the molar mass of arsenic? Well, that's a great question. The answer is, for this route, I didn't need it, right? Because the formula for parts per million gives us grams per milliliter, and I'm just using what they gave me for concentration to deduce how many grams that would be in a milliliter. And when I go to percentage, all I need is grams and milliliters. So I don't, the molar mass of 74.92 grams per mole is not going to be necessary unless I want to know the number of moles, right? Because already parts per million is talking about a ratio from grams. So if you remember what the formula is, then you can plug it in. Now, I'm glad you brought that up, Joyce, because now I have grams and milliliters and I need molarity, and molarity is moles per liter. So now, in order to get my concentration in the right units, I do need moles. Now I need molar mass. Okay, so I'm at grams per milliliter. How do I convert to moles per liter? You guys help me out. Start with where we're at. 10 to the negative 8 grams of arsenic. Milliliter of solution. Do I put that molar mass on the top or the bottom? Bottom, because you want your grams to cancel. Perfect. 74.92 grams of arsenic in 1 mole of arsenic. Excellent. Now I have moles on top. What else do I need to do? Perfect. I need to go from milliliters to liters. So 1,000 milliliters in 1 liter cancels. Okay, I did both of those things because when I asked for molarity, you guys instantly recognized that what I really wanted was moles on top and liters on bottom. So you said, no problem. I know how to go from grams to moles. No problem. I know how to go from milliliters to liters. And once I do both of those things, I have moles per liter, and hey, look at that. I'm done. Yay! Now I just plug it in. So I have 1 times 10 to the negative 8th grams of arsenic, and that's right here. Divide that by 74.92 grams of arsenic in a mole. Multiply that by 1,000 milliliters in a liter, and I end up with the value of 1.33 times 10 to the negative 7th. Okay, 1.33 times 10 to the negative 7th molarity. Okay. If that looks astonishingly tiny, that's because it is. And that's why we're using now parts per million instead of molarity, because nobody at that point wanted to use 10 to the negative 7th. They said, that's crazy. I'm just going to use parts per million because that's a concentration unit that makes the most sense for this level of concentration in my sample. Okay. All right. This chapter, as you have seen, is an interesting mix of some dimensional analysis. Let me just get my units where I need them to go, and some formulas that you guys, I'm not going to give them to you, so you guys are going to need to know them. So being able to be fluent in both and fluent in translating between when do I need to use my formula, and then when can I plug this into a different formula, or when am I going to need to use dimensional analysis, that will be helpful. Okay. Any questions on this section before we move on? Okay, I'm going to stop this recording.